Okay, so after we discuss the basics of hashing, we want to discuss about hash functions. Okay, so hashing, um, in the hashing, what is important is the simple uniform hashing, which is a concept where we said that all the incoming keys are likely to go to any of the open slots, independent of where the other keys are being hashed. So it's the concept of simple uniform hashing. Now, one thing I want to tell you that this choosing this hash function, this concept is in Corman book chapter section 11.3. So all such information about where from you have to read, it's in the syllabus page with all the individual topics and where from you have to read. But here also I mentioned so that it's easy for you to find. So in my book, which is the third edition of algorithms book, it is in the section 11.3. Okay, so now this concept of simple uniform hashing will be realistically possible if we knew the probability distribution of the incoming keys, and then we can really achieve the simple uniform hashing. But because most of the time we do not know the distribution of the incoming keys, what we are trying to do, we use some kind of heuristic strategies to which will give us as close to the simple uniform hashing as possible. One of the there are two methods. One is the division method, one is the multiplication method. The division method is I'll talk about the division method. Before that, I want to tell you that what are the thing we are looking for. As I said, that we want to achieve simple uniform hashing, as close to the simple uniform hashing as possible. So the hash function, what we are trying to choose, to simulate the concept of simple uniform hashing, should distribute keys uniformly into slot, as uniformly as possible. Okay, that irrespective of other keys where they are being hashed. Regularity in key distribution should not affect uniformity. What is the meaning of that? So that means each slot is equally likely independent of, the regularity in key distribution is independent of any pattern on the incoming keys. If the keys are coming in a particular pattern, it's not necessarily we have to kind of store it in that pattern. They can still go to any location in the hash table depending on the the hash value being generated. Okay, so each slot is equally likely for all these incoming keys, even if they have some pattern. So that is called the regularity in key distribution. Okay, regularity in key distribution is like some kind of pattern. It's like a pattern in key distribution. Pattern in key distribution should not affect that concept of uniformity. Otherwise, the simple uniform hashing concept will be damaged or will not be properly used. Now let's see the division method, which is one of the method which tries to achieve this simple uniform hashing. What does it do? It's very, very simple. It says generate the hash function using the k key modulo m, where m is the the size of the table. So map a key k into one of the m slots. M is the size of the table, that means that many number of slots, and modulus function we use, so k mod m. Now here this choosing this m is a little bit tricky, because if you choose m with a small divisor d, like d equal to 2, then m is becoming an even number. And if all the incoming keys are also even, then what will happen? If the m that means m is even, means the number of slots in the table are even, like suppose 10 slots, and this you dividing with like 2. Okay, so only what is happening, only the even number of slots in the table will be filled, and the odd number of slots will never ever be filled. So it's not a proper distribution. Okay, so it's kind of violating the concept of simple uniform hashing. All slots are not being equally likely, so only odd slots are being filled, even slots are not being filled. So suppose m equal to 2 to the power r, and all factors of m are small divisor, like 2 to the power 5, suppose 32. Okay, hash will then not depend on all bits of k. Okay, only if m equal to 2 to the power 6, and suppose this is the key value, incoming key value, then it will actually be considering, if when you do modulo to the power 6, the last 6 bits of the key value will be considered. I mean, whatever be the, if this part is equally generate equally likely all possible combinations, then that will depend, the simple uniform hashing will kind of depend on the mercy of this part being equally likely. But whatever the other side of the remaining bits of the key, it's not being even used. If you know that if you include more bits, then the variation, then the chances of this concept of pseudo randomness will be more. So we cannot just lose this part. So if it's just a power of 2, this is difficult to guarantee that all the bits are being considered, and the concept of pseudo randomness, the simple uniform hashing are being brought into the picture. So what is the idea? We try to pick m to be a prime number. Okay, prime number in the sense that it should not have any common factor with k. Okay, to number not too close to power of 2 or power of 10, like 10 square or 10 cube should not be too close to that. Power of 2, 2 square, 2 cube, 2 to the power 4, 2 to the power 5 should not be so close to that. Otherwise, it's just only the last few bits will be considered. So we choose m to be a prime number, not too close to the power of 2. Suppose there's some examples in the book like 701. So this is a good value of m, where where this is a prime number, this is not close to any power of 2 or power of 10. So this kind of gives a good value. So as I said, it should be prime number, no common factor with k. Okay, so this is the division method. Division method kind of depends on the how you choose the m. If you choose the m in a very naive manner, there will be a lot of hash collisions and many of the slots will not be filled. So that will result in violation of the simple uniform property. Okay, there is another method which is the multiplication method, which is a two-step process. So there's a hash function h of k equal to m times k a mod 1, and you take the ceiling of that, okay, floor of that. So and a is here actually with respect to this description, a is a fraction. If you see the slides I'll share, they write it a little bit different way and say that a is an integer between 2 to the power w and 2 to the power w minus 1, where w is the word size of your computer. If you don't remember what is a word size, I already talked about when we talked about the RAM model. Word size is the number of bits which being taken from memory to processor at one time. So that's the kind of, you say, the size of the path, size of the bus. Okay, like you say it's a 32-bit computer, so your word size is 32-bit, means one word in memory stores 32-bit. 64-bit computer, one word in memory stores 64 bits. Okay, so now you see that here it says k times a mod 1. Okay, a is a particular constant, k times a, k is the key, so we multiply k times a mod 1. This is meaning actually the fractional part of ka. Okay, so it can be written like that also. It's like ka minus this just the, so we subtract the proper part, and then what remains the fractional part of ka mod a means, and then you multiply m with that. But m here is not like in division method, selecting m was a critical, the value of m was critical. Here m is not that critical. Okay, so choose m to be a power of 2. You can choose m to be a power of 2, m equal to 2 to the power p, where p is an integer. Okay, so like 2 to the power 5, you can see 5 is an integer. And suppose the word size of the machine is w bits, and assume that the key will be fitting into that. Okay, key is not more than w bits, and a is a fraction in the form s by 2 to the power w is divided by 2 to the power w, where s is less than 2 to the power w greater than 0, where s is an integer. Okay, that reformatting of that will make a an integer within the range 2 to the power w to 2 to the power w minus 1. 2 to the power w minus 1 to 2 to the power w rather. So now you see what we are doing actually. we have the value of k fitting in w bits, that is this. We have the value of here, this is s, which is a times 10 to the power w. You see this s is a times 10 to the power w, so this is this, so that's why a will be within 2 to the power w and 2 to the power w minus 1. And now if you multiply these two things like in here, so what will happen, this will is a w base, is also w base, together they will produce the result, which is 2 w bits. Okay, 2 w bits. So 2 w bits, and this is the lower the less significant bit portion is the most significant bit portion, or less significant word, or more significant word. Now what we do in this we are actually trying to shift this, right shift this, for we do not consider this upper part. Okay, so upper part is not considered in this lower part, the least significant w bits. We take w minus p bits, we right shift. Okay, so this is w minus p bits. So this is the p bits, we need that p bits. Okay, more significant p bits, because m equal to 2 to the power p. So that is the part of interest. So it's also represented like that, h of k equal to a times k mod 2 to the power w, and right shift w minus p bits. So RSH is a bitwise right shift, and which most of the computers already support. So it's much easier. So multiplication method executes much faster in computer than division method. Okay, so it's written here faster than division method, because most of these operations like w bit multiplication, right shift, this can be done in most of the computers very easily. Okay, so let's see example where m equal to 8, which is 2 to the power 3. Okay, so m equal to 2 to the power 3, so p equal to 3. You see, m equal to 2 to the power p, where 2 to the power 3 is 8, so p equal to 3, and w is equal to 7. That means the 7-bit computer. Okay, so now assume that a is the incoming, a is the constant. Okay, so it's fitting in w bit, in the format is this, and k is the incoming key. Okay, k is the key, so this is this. So when we try to multiply this a and k, and what is happening is that so do not directly match with this. This is this model writing here. So this is actually the a's value represented in the form of s. That's why this is like that. So here a and k we are multiplying, and so then what happens? This is the 2w bit result. Okay, so this is w bit, this is w bit, this is 2w bit. Then we actually multiply that with m. If we multiply that with m, what will remain is only this part. Okay, the lower order w bits will be there, and among that we do this right shift of w minus p bit. So w here is 7. Okay, there's the word size, and p is the power in the m, like 2 to the power 3 power of 2. So that's p equal to 3. So w minus p is 4. Okay, you right shift by 4 bits. If you right shift by 4 bits, this 4 least significant bits will go out of the picture. So what will remain among this w is this part 0 1 1. So that will be the hash value returned for this particular key. So this is the way the multiplication method works, and this is faster than the division method. And most of the time we actually show using the division method in this class. When we see the examples and other thing, we'll mostly use the division method. This is a little bit difficult to understand, but this is also an important method. So I covered it so that you guys at least know what is the concept, but most of the time we'll use the division method.